Hello everybody, welcome to Abacus Tutor Workshop 1, and in this workshop we have three different analyses: thermal response analysis, structural response analysis using beam element, structural response analyzing using cell element. So in fire analysis, first is to perform the thermal analysis to determine the temperature distribution in the cross sections. And after that, we perform the structural analysis either using beam element or cell element and also solid element. But in this project or in this tutorial, we are not going to discuss about the solid element. And we have the problem here, the problem descriptions. So a simply supported beam made of I-beam is heated with the horizontal burner in three sides and and four concentration load at 4 point. These points are applied, and these four concentration load are equivalent to the 42 kilonewton, which is total load applied, and which is equivalent to uniformly distributed load of 10 kilonewton. And this fire test is taken from the literature from Cong. And first, and in temperature analysis or in thermal analysis, we obtain the temperature distribution in the beam cross sections. And that's why the first tutorial for this workshop is thermal response analysis, and we have already gone through this one. So the first video tutorial is the thermal response analysis. And in this tutorial, we are going to perform the structural response analysis using beam element. And after that, we will perform the same structural response analysis of the same, this simply supported beam using cell element. And this is the structural response analysis workshop using beam element. And before uh, going to model that one, so first we always start with the part model, and in the part model we create the 2D geometry here for this case, and you can also create the 3D domain, uh, but now let's create the 2D geometry. And the beam is modeled with a line of length 4200 millimeter with beam element. And and in this here the coordinate of the point, so this is first point and this is first point, and this is the second point, third point, fourth point, fifth point, and sixth point. So these are the coordinate of that point that we will use to model the line. So we will create the line between these 2 points, so it's easy to apply the the boundary condition in this to support and also the force. So it will be easy to apply that force there. So that's why we create this coordinate and then create a line uh, between these coordinate and then the total beam of the length 4200. And now we move to abacus, and this is the abacus environment. And now let's rename this model file as the structural beam, which means that we perform structural analysis using beam element. So let's model, and also I like to import the this 2D temperature analysis, and these three files you can download from the descriptions provided in this video. So these are the input file where you can see the ready-made solution for this case. But this 2D temperature is the temperature analysis, and we can import this one for when we need to obtain the temperature curve from the thermal analysis and also the material data. So we can copy the data from here directly in this tutorial. Okay, so let's import this 2D temperature, and then we have that one, and then let's create a job here, and now let's create a job. Let's 2D temperature, and let's name it as 2D temperature thermal response. So let's make it this as a thermal response, and the model. So we have two options for the source, so either the input file or the model, but now we can say this is the model and this 2D temp is the model. We continue, and now for the job setting, I like to use more processors, but you can choose yourself how many processor you like, and then we right click here and then submit the job. And we can also monitor the result in this one. So the idea here is to see the result from the thermal analysis, which we are going to use for the structural analysis. So the temperature distributions in the beam cross section is obtained from thermal analysis, and we take this temperature from this one point and then apply that as a temperature input in structural analysis. Okay, so let's now go to the beam. So from here, beam. So now first part is to create the part here, and now to create the part, so we can enlarge this structural beam tree under the models. So we have these two models here. The first is the temperature analysis of the beam cross sections, and this is the structural analysis of the beam using beam element. And here everything is empty, but so now let's start creating a part, and then create part. So let's say part is beam, and then we choose the modeling space 2D planar. We can also do this one as a 3D, but for this one let's simplify to the 2D planar and type deformable, and then base feature. Now we are going to model this one using a line, so beam, which means that we have to select the wire, and this approximate size for the sketching dimensions, so we can say maybe 8500, because 4200 is the length of the beam, so we can choose that one. Okay, now we have this modeling space there, and now we have different tools for modeling the geometry. So let's start with creating a line, and then we, for the line, we create using this coordinate, so we can directly input the coordinate of this point 1 2 3 4 5 6, and then we can create the line. There. So let's start creating the line. So the first point is 0 0, so let's only give 0, so it will take only x, no need to give y, but if you like you can give y also. And second point is 5 to 5, the third point is 1 575. Fourth point is 2625, and the fifth point is 3675, and finally the, another point further is 4200, which is the total length. Then then now we press escape, and then we model the line, and we can also uh, this auto fit view in order to make the sketch auto fit in this sketching window. And now we have create a line of 4200 millimeter, and then we can now accept this drawing. So let's uh, click on the done. Now the geometry is created. Okay, so we have create a part, and now next is to define the property for the material, beam sections, and creating the beam profile and assigning the beam orientations. So these are done in the property models. These are done in the property models. And for the defining the material properties, we need to follow the unit. And in Abacus, we doesn't follow the unit, so we have to use the consistent unit system in Abacus. And in all the structural analysis in this tutorial, we are going to use this SI units in millimeters, and then the force is in Newton, and the, this this mass is in ton, stress in megapascals, and density in ton millimeter cube. So this is the unit system that we are going to follow in this Abacus tutorial. Okay, so the mechanical properties: density, temperature dependent isotropic elasticity, temperature dependent coefficient of thermal expansion, and temperature dependent plasticity are defined according to the Eurocode EN 199312. So, but you can further regarding this data, you can define in from the input file that is given in the link descriptions. So you can copy and paste the temperature and the material data from there. Okay, so now we have finished the part model where we create a geometry, and we can look it from here that we have created a beam, and then the beam using a wire fetcher, and if we like to edit our sketch, we can edit like this. Okay, so let's done this one, and then now let's let's go to the this property model, and here we have the option for creating the materials, and also this material manager, and then creating the sections for the beam and section manager for the beam, and then we have this assign section manager also. Okay, and here we have this option to create the beam profile. So let's go to create the material here first, and we create, okay, let's name this as steel, and if you like to put this description of the material, you can have this one. And for the material behavior, now for the structural analysis, what we need the density, which is from general you can get the density, and then we need the elasticity, and we can get from mechanical elasticity and elastic. And then also we have to have the plasticity definitions, and for that one we get from mechanical, elastic, and plastic. And also we need these expansions of the thermal expansions. So basically what we need is the density, and then the temperature dependent isotropic elasticity, and then temperature dependent thermal expansions coefficient, and then temperature dependent plasticity. And these are all defined according to the given Eurocode code. Okay, so now let's start defining the density, and you can copy and paste this the data of the density from the previous from the given input file, and then the density is nothing but we can just copy and paste from that that data. So and then elasticity, so in the elasticity we have to use this isotropic here, isotropic type, and then use temperature dependent data. So it means that we have the Young's modulus, the Poisson ratio, and the temperature. And you, for the data, we can take the data from the input file and then copy and paste. So this is the temperature dependent elasticity, the Poisson ratio versus Young's modulus for different temperatures. Okay, and then expansion. So this is also isotropic, and we are going to toggle this use temperature dependent data. And for that data also we do similar. We copy and paste from the input data that is provided to you. Okay, so and now we need to define this elastic plastic data, and also this is also temperature dependent, so we need to toggle this temperature dependent data, and then from the from the input file we can just copy and paste the temperature data for this one. So here we have for the 20 degree we have defined first the true stress versus strain data, and then similarly for 100 degree and for different temperatures. So the data can be copy and paste from the from the input file. Okay, and now we have defined the density, elastic, temperature dependent elasticity, temperature dependent plasticity, and temperature dependent coefficient of thermal expansions. So the material is ready now, so we expect this one, and we can see here we have created a steel, and then we can also review the material behavior, density, elastic, plastic, and expansions. Okay, so we have created the material data. Now we create the section, the beam sections. So now here section, so section, that's okay. So this is beam section. We can write this beam sections, and in the category we are doing the beam sections. In the type we select the beam here. Okay, continue there, and now this window appears, beams, edit beam sections, and here we have name, that's the beam sections, and the type beam. And now we select this default section integration during analysis, and then profile name. Now we have not created the profile name, so we need to create this profile here. So this is I-beam profile. We can name I-beam profile, profile, and it is I-beam. Okay, continue, and then we have to give the I-beam definitions. So let's let's take the data. Let's take the data from this previous from the input file. So we have this we have the data. So now here, so let's say 0 this I, and 250, 125, 125, 9, 9, and 6. So these are defined according to the given dimensions. So here are what is I, B, H, B1, B2, and then we follow that one and define the I-beam sections. Okay, and then we accept. So we have this I-beam there, and then we have to define the material. So we have created here the material E-stills. So E-stills, and then position ratio, and also we need to define the section position ratio there, but now we say we leave it default 0 there, and now now the most important is the temperature variation. So we are going to give the uh, temperature in the temperature point in 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 beam element. So we interpolate from the temperature points. We select this one, interpolate from temperature points. Okay, so we have create the sections and also the beam for that one. And now we have create the materials. We have create the material steel, and also we have create the sections, which is the I-beam, and with I-beam profile we have also assigned the material definitions. Now we have to assign that created section to this line geometry. So now we assign section here, and then now here you have this option create set or sets. So let's untick that one and sets, and let's say we don't have any set there. So means like let's create a set. So let's say this is beam, and then let's select this all with we select this all. And now how you can select is that uh, the left mouse button, and then you click and then you drag. Yes, and also now we can select this first part and the control, and then shift second part, third, fourth, and fifth. So in selection of this this geometry to assign a section, so if you take the mouse over there, it will come to the red, and then click that one and press shift and click like that, and click continuously this all part. But other reason is that you can just left click the mouse and then drag over the geometry, so it's all selected and then done. So it means that we have this beam region here, which is this red, and we are going to assign this beam section over this point, and then we select OK. Okay, one is assigned, so we don't want that one now. It's assigned, so we have already assigned. We can check that we have assigned this beam, and you can highlight that also. Okay, let's dismiss this one and cancel this one. Okay, now next is the assigned beam orientation. So now we have already created this set, so we can go in the set, and we have this beam, and then continue. So this like here we have assigned the section, so it's pointing all in one directions. So now we accept this. Here it's the same, we don't need to change these tangent vectors there, so it's okay. And now we approve that one. Okay, and then okay, so now let's cancel this. So we have assigned the beam section, and now for to confirm that, we can go to the view, and then there's a part display option, and where you can have this render beam profile, then apply. So it shows the beam. Okay, this is correctly. And now we have done this in 2D, so we cannot rotate. But if we have done this in 3D, we could rotate. But now we have defined the part module. So we finish this part and the property for the beam. Okay, and the next one is the assembly step, load mesh, and that kind of models. Okay, so far we have defined the part. We have in the part module we have created the geometry, and then we have assigned the sections and the material in the property model. Now we will define the assembly. So in each Abacus analysis we have to define the assembly, and then we apply, and then we will define its steps and other parameter according to this workflow. So now let's start to create the instance, uh, and then that is done in assembly model. So so we go to this assembly model, and 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 now we are in assembly model. We have created this already part model and now assembly model. So let's click the create instance, and then so we are creating instance from the part, and the beam is the part what we have model. And we have this two type of instance, dependent mesh parts or independent mesh instance. So we have this simple structure, so now it doesn't matter how do you mesh on part or instances. But when we have a complicated structures, then this type of selection will help us. But now let's say okay, we mesh in part, and then we apply, and then now the instance is created, and you can see that a coordinate system is created from 0 there. So there is, you can see. Okay, so now we can see, and the assembly is created, and you can see that this beam part, this assembly is created. Okay, so we have created the assembly of this one, and you can see that a datum coordinate system is this. This is also created in this one, in the 0 positions. Okay, so now we have created the assembly, and now next we need to create this. We need to go to this step module. So in the step module, we uh, create we create we create the static analysis process using a explicit dynamic analysis procedures, and then we have the model setup and analysis, and then create the output request there. So in Abacus, so the basic structural analysis procedure is that we we first do the post processing. So define uh, all the parameters that are needed in the material data, geometry, everything, and then we solve that one in two steps. So two explicit dynamic analysis step are needed. So in the first step, we apply the mechanical loading to the structures, and then in the second step, we apply heating due to fire, and then finally post process the results. And now for the model analysis and the setup, so the structural analysis is performed using Abacus explicit dynamics procedures, and we know that the real temperature scale using the fire test experiment is very long event, usually from 0.5 to 1.5 hour. So when we are using this explicit solver, we have we cannot run these long simulations. So therefore, the simulation time can be scaled down and scaled down from the actual simulation time because of its quasi-static nature of loading and heating process. So it doesn't affect. So we reduce the total simulation time by a scale of 100. So usually for the usually we do the simulations for 18 seconds. So that's which is equivalent to 1800 seconds. For the 1800 uh, total duration of the time, we scale with a factor of 100. So and then perform the explicit solution using two-step. And now here we see that we have this load curve for mechanical loading and the curve for the temperature loading. So it means that in the first step we apply the mechanical loading and usually around these 2 seconds, and then for the this duration, and then for around these 18 seconds from here we apply the uh, temperature due to the fire. So the structural analysis is performed using two steps. Okay, now let's go to the abacus, and in the abacus we now go to the step model, and in the step model, so in the step model we need the initial step is created automatically. So we need to create this two-step step, this mechanical loading step and the fire step. Okay, so let's create that one, and now let's create this one. The first step is the mechanical loading step, so I name as mechanical loading. And then now here the solution procedure is dynamic explicit. We select this one and then continue, and now the first is around 2 seconds we apply the mechanical loading, and we always select this non-linear geometry on. Okay, and then we leave this most of this one for this tutorial video. We leave this default. Okay, so the mechanical loading step is created. Now let's create the second step. This is fire heating step. So fire heating step, and this is also this dynamic explicit procedures. And now this is around 18 seconds, and this non-linear geometry is on, and then we leave the other defaults. Okay, so we have these two mechanical loading step and the fire step created. Okay, so let's dismiss this one, and now let's say we see here in the steps, and also in the step manager we can have a look that we have created mechanical loading and firing steps, and we can edit that one. So the fire time period 18 seconds, and then this one is 2 seconds. So we have created this one, and the next one is this other load mesh and job. So we can move forward now, and then now we have to create the load now interactions. So we don't have any interaction now in this one, and because this is simply supported beam structure, so we have the boundary condition into end of the beam, and then we apply the 4 concentration load. So let's jump to the load, and then we have this in the load. Now we have to create a load, then we have to also create boundary conditions, and then we have to create a predefined field, and the temperature due to the fire are assigned in the predefined field. So we need to create these three things here: the load, the boundary conditions, and the predefined field. In the predefined field, we will create the temperatures, initial temperature and the temperature due to fire in the beam cross sections. Okay, now we are in load module, and in this module we will create the mechanical load, and then we create the boundary conditions, and finally we create the predefined field. And in this analysis, the predefined field is the initial temperature and the temperature due to fire. Now for the loading, for the mechanical loading case, the beam is loaded with 4 concentration point force in y directions as shown in this figure, and simply supported boundary conditions are defined for the in nodes here, or these points, in the both points. And now we have to apply the load with reference to the amplitude curve, and now the load is applied for 2 step. We have already created the first mechanical loading step 1, and the second step is the fire heating step. So now the load is applied with reference to this load curve, and in this load curve, for the first step, the load is increased from 0 to 1, which is maximum. So in first steps, the mechanical loading is applied, and then the load is kept constant from the second steps. So the first step is the mechanical loading step, and the second step is the fire heating step. And similarly, the temperatures is defined initially in the first step, which is around 20 degrees Celsius, and after that in the second step, the temperature loading due to fire is defined. And now here in the step 2, for temperature loading due to fire, we obtain this curve from previous thermal analysis. All right, so let's start first creating mechanical load, and then boundary conditions first. So let's move to Abacus now. So so uh, so in the Abacus, uh, now we are in the load module, and then we have create load option here. So let's create a load, and let's name the load as mechanical loading. And now we have to specify, we have these 3 procedure here, these steps. So we apply this mechanical load in mechanical loading steps, and the category is mechanical, and you have different this type of force that mechanical load you like to define. Now we choose the concentrated force, and then continue. So now here we are applying the mechanical load in these 4 points, and we are applying the same load there. So let's create a set up those point, and then let's say we say loads point, load loads point, load points, and then let's select these 4 points. So if you just take your mouse in this point, it will turn to red, and then you can select the first point is selected. And now if you take this to another point, the mouse there, it will come red. So now to select the multiple entities, we press shift and then select that one, and similarly select other 4 points. So 4 point is selected, and now we're done. So now here this window appears. So mechanical loading, concentration force in mechanical loading steps, and then we define this in load points, these 4 points, and our coordinate system is global. So we follow this global, and here is so now the distribution of the force is uniform, and then we have this C concentration force 1 and concentration force 2, but now this 1 is x directions and 2 is y directions, and we choose this our case in 2D, so we don't have the CF3 in this. And now we define the mechanical load. So this is 0 in this case, and in y direction we have this minus 10.5 kilonewton. So we follow the SI unit, so minus 10500 newtons applied. Downward negative means minus, and then it is the amplitude is follow with uh, with reference to a mechanical loading curve. So now here is this create amplitude. So we click in the amplitude, and then we define this as mechanical loading curve, mechanical loading amplitude curve. Okay, maybe let's say curve, and then we define this as a tabular. There are many options where you can define, but now tabular, and then we continue. And here we like to define over the total time, and then so in the beginning it is 0 0, and at 2 seconds it is following maximum, and then at 18 at 20 seconds it is following also the maximum. So we have defined this curve, so which means that uh, here we have defined this amplitude curve. So 0 0, and here it's at 2 seconds it's 1, and similarly at 18 seconds it is 1, because we have defined 2 steps, and we solve those. This first step is the mechanical loading steps, and another is the heating steps. So we have scale our simulations to 20 seconds, and now let's click OK. So you can see here that we have created this curve, mechanical loading, and then now we select this mechanical loading curve, and then okay. So 4 point load is created, and the point load is applied with this amplitude curve. So in the beginning we have defined this load here, so it will follow that and multiply this with the amplitude of the curve. And now here you can see if we go to this load manager, so the mechanical loading step is created, and here in the mechanical loading, and it is propagated. So here it's propagated uh, uh, through in heating also, so it's kept constant. Okay, now then we defined the these boundary conditions, because there is only this one concentration force applied at these 4 points. Now we have to define the boundary conditions, and in order to define the boundary conditions, so we have to define in this left and right. So let's create the boundary condition 1, and let's say this is this left left pin, so pin left pin, and this is also applied this in mechanical steps, and we select this displacement and rotations here, the boundary conditions, and then we continue. So we create the set. So let's say this is left pin, and then we select that left pin and done, and then this window appear. So here it is here we fix the x and y, so no displacement in x and y, and we give the free the rotations, and it is so we okay, we accept this one now for the left side, and then we have to create also for right. Okay, so now we can check this defined load here, and so I have now this move. So it was initially at this point, and I like to move this boundary condition to the initial step. So move left, so it's created in the initial steps, but in the just before we have created that in the mechanical. So but let's change to the initial step. So from here you can change to move left or right for different steps. Okay, so let's create another boundary conditions at the right support. Okay, so roller support, and now let's create in the initial step and the mechanical and same displacement and rotation. And now we continue, and this is we select, okay, this is left, so we can rename this as a left, and then down, and now here it doesn't uh, move in y directions. We fix that one, but it's allowed to move in x direction and rotation in z UR3. Okay, so we have now fixed this this we have applied this to, and also now, for example, if we go here, this mechanical loading other steps, so you can see that this boundary condition is applied, and then we have also applied the 4 concentration force, and we have also create the mechanical loading curve here. The next one is now to create a predefined field, and and to create a predefined field we follow this approach, where we first define the initial temperature in step 1, and then we define the uh, temperature due to fire, which is the result of thermal analysis in step 2nd. So here we have these two tasks defining initial temperatures and then temperature due to loading due to fire. And these results are obtained from the thermal response analysis, the first tutorial video. All right, so here is an example of the 2D temperature analysis. So we have this beam cross sections, and then we obtain the results from here, and then apply in this step 2. Okay, so here is the results from the annual report of the project. Uh, Here we have these different temperatures in the wave, flange, upper and lower flange, and they are compared with these literatures. And we need to define this temperature uh, curve. We need to define this temperature curve for the in the predefined field. And the temperature curve, we follow this one. And in Abacus, the method for defining the temperature loading after thermal response analysis, we have several methods, and one of the method is defining in beam and cell sections. So it means that in this method, temperature histories are assigned to beam and cell section definitions. And for cell, the temperatures can be assigned as the reference surface of the cell or gradient through the thickness for non-uniform temperature distributions. And similarly, for beam element, the temperature can be input specifying the value at origin of cross section and defining in the gradient in the beam local directions, or directly specifying at particular point in cross sections. And amplitude can be defined using an amplitude parameter which varies with time. And for the beam sections, it should be noted that only one single amplitude can be specified. So here in this workshop 1 of simple beam exposing fire, we define the temperatures in uh, in in temperature points in beam cross sections, and then we define one amplitude of that point which varies with time, and define the temperatures. But there are other methods also where you can define differently. But for the beam, we follow this one in this example of the tutorial. Okay, so now we define it in the temperature points. So the temperature points are these points where we define the temperatures of the amplitude curve. So for the thermal response analysis, okay, so for the thermal response analysis, we have obtained the temperature like that, and we define, okay, this is in the wave. So in the wave here, this is the temperature 2, and we give this one, and with scaling we define at a 0.3 and 0.1. So this is beam in plane examples. So we have 3 temperature point in beam in plane, but in case of beam in space or in 3 dimension, we have 5 temperature points. And when we define the 5 temperature point, we can only use one amplitude curve. So either take the temperature of this point or this point or this point or that point, and then multiply with the factor of for the same curve and obtain and define the temperature at other temperature points. But now here we are doing these examples and now we are defining one temperature point and then giving the scale factor for this remaining two. And now the first step, this was the first step where we perform a thermal analysis, and from the thermal analysis we have obtained the results, and we can take one curve from here and then scale that one to our simulation time. So we have this 0 to 2 seconds. We have this mechanical loading step, and from 2 to 20 second, which is around 18 second, we have this heating effect. So this temperature curve, what we have obtained from this thermal analysis one, it has to be scaled to that one. So we divide by 100, and then for 18,000 second, we scale it to 18, and then we choose one curve, and then that one curve will be applied in this third step. So if we think this is second step, we applied in that one. Okay, now let's go to Abacus. So let's go to the Abacus, and in the Abacus we now have to go to define the predefined field, and now let's say this is fire heating, and this is defined in fire heating step. So in the mechanical load we apply mechanical loading, but now in fire heating step we apply the fire heating, and this is other category, and the type of selected is the step is the temperatures, and we continue. And now the temperature is applied in the whole beam, and we have already create a set, so let's not create the new one in the set. We can see here the beam, and here if you had not toggled this highlight selection in viewport, you cannot see what is the sets. So let's say, for example, here if you have selected this one, it means that whole beam is selected, and if you say left, then the left is selected, and so left. So actually this should be right. So left pane, and here is so left pane, and here left and load point. So let's rename that one. Now let's cancel this one, and now we can go to the assembly here. Under the assembly we have set, so this is beam, whole beam, this is load points, and this is left pin, and this is left pin, and this is right roller. So let's rename this one, and then put right, then roller, roller, roller. Okay, so, and then we also need to go to this boundary conditions and then edit this roller option because we changed the name. Yes, so here it should be the roller, this point, and continue. Yes, that's the same definition. So sometime when you need to rename the different entities, you can follow this approach. Now let's check one time. We have this mechanical loading. Okay, it's there. We apply in load points, follow the mechanical loading, check the value. That's all right. And then let's go to the boundary manager, and then we have this left. So it is this right loader option. We have that, it's okay, and the left in we have here this left pin, and X and Y are fixed. Okay, now let's go to define the temperature field, and in the temperature field, so let's write fire temperature, fire heating, and then it is created in the fire stage, and it is temperatures. Continue, and then we select this is applied in the whole beam, and then we continue. Now here the temperature distribution is, we have different option here, but now we specify as a direct specification, and then this is not constant through this sections, but we define at cell or beam temperature point. So we define in temperature beam temperature points, and we have defined this problem as this problem, which means that we are going to define this 1, 2, and 3 temperature point in the beam, and that's why we need 3 temperature points, and then we need to also define the amplitude curve, and the amplitude curve is the system. Look, let's write fire temperatures, fire temperatures, and tabular, and this is also applied in total time. But now we can take the temperatures, amplitude of the temperatures from the input file. You can obtain the value from there and just copy and paste over here. So we have this amplitude from the input file, so we can just copy all from the input file. So here the idea is that you can obtain this value if you import the given input file in another Abacus windows, and then you can just copy and paste this amplitude. So copy this, and then we can paste. So here, at time 0 it's 0 amplitude, and then also 20 0. So and now here we have this start from the mechanical step here up to 2 seconds. Now after 2 we apply this temperature, and the temperature now here is scale to 1 and now here, so that's why we multiply with this curve, this scale curve, with the temperature of the maximum temperature of the point in this wave and the flange of this one. So we specify the temperature 1, 2, 3 in the point and multiply with the curve. Okay, so now let's cancel this one, and now we can see here that from the previous another window we have given the 3 different temperatures there and multiply with the curve. So let's specify the temp point 1, and here the point 1, what is the point 1 is, the point 1 is this point. So for that one we define the temperature, the maximum temperature is 745.5 723, and now here we can define this as 739.47, but you can ignore this value, but let's define 719. And now here we have to now select the amplitude curve, and for that one we select the fire temperatures, and we now accept. So the temperature is assigned, and also now we need to assign, this is now also assign the initial temperatures. So here if we open the predefined field managers, we can create the initial temperature step, the initial, and this is the temperatures, then continue, and this is same like whole beam, and then we define with at temperature points, and we have 3 sections, and then it is 20 through the those points. So that's okay, and here you can uh, so it's defined, uh, and now it's, we define the initial temperatures there, and now we finish this load module, and we now go to the mesh module. So in the mesh module we create a mesh and assign the element properties here. So let's go to the mesh model now, the mesh model, and now here first we need to seed the part. Here are different meshing options. Here you can explore that yourselves. Now we seed the part. So now it says that dependent part instance cannot be edited or assigned mesh attributes. It means that we we have we have to select these ones. Now we have render this beam, so we can off this one. So part display option and render, if you off this one, so we can see now that one. Okay, then seed part. So here the approximate size. So we can select what is the approximate the mesh size for this one. So let's say 90. This means that we have these elements there, 90 elements. We have this approximate global size of this one is 90. Okay, you can choose the appropriate sizing control, but now for this tutorial we can leave it as this 90. This is random value. Then apply. Okay, and then we need to now assign the type, element type. So we select that one, and now here the beam, for the whole beam we need to assign the beam element type. So now here we need to choose, this is explicit dynamic analysis, so we toggle the explicit button, and under the family of the element we select beam, and the geometric order linear for this case, and we leave this as default. And the main thing to note is that we have selected B21 or two node linear beam in plane. So if we have done this one in 3D, then the beam 31 or two node linear beam in space. Okay, then Now we dismiss this one and select a region to assign mesh. So done. And now we need to mesh part. Yes, so it says that 48 elements has been generated on beam here. So we can inquiry this one. So let's inquiry mesh and the entire part is done. So it has 49 nodes and 48 elements, and the element type 48 linear, element of type B21. We can see that one from the query tool, and the query tool can be this I query informations. Okay, so the next module is a job module, and we have defined all the necessary information that is needed to model the structures. Now the pre-processing is finished, and now we are going to solve that one. So in order to solve, then we need to create the input file and then run the job. So to do so we have now we go to in job module, and then we create so if I take this away, then we have this job, and here we have this thermal response completed. I have run this one before, and we create similar like that. And now let's go to this create job, and this is now a structural beam structural analysis using beam. And you have the source. The source is model or input file. In this first case, we give the input file as a input file, but now we select this model, this structural beam, the model. So it will create the input file from this model, and then we run. So then continue. Then now we see that name is structural beam. That's the name of the job or the input file, and then it takes the definition from the structural beam model. And now the analysis is the abacus explicit, and now we are doing a full analysis. And here for fast, we can increase the CPU as necessary. Now here I do with 8 CPUs, and precision now I leave it as a single, but we have this other double and single precisions for the solutions and also for the nodal output. But now we keep it simple and make it single precisions. But now I only change the CPU so that we can finish fast solutions. Okay, now we have this finished this one, then we can go to the job manager, and we have this structural beam, and we have now we can do first the data check, and then it start for the data check, which will see if we have some mistakes or some keyword definition wrong. Then we will have the some error message there. Now we can see the status here, and here we can see that the job structure has been completed. So check is completed. So we can now submit this job. So let's submit the job, and yeah, job file already exists in, yeah, so in my case there might be some old run file, but you can override that, like we can override that one, and then we can run this one, the structural beam, and now it's running, and then we can uh, monitor that one here. So we have this data file where you can see different the status file, so different status of different, so and then so the abacus explicit is started, and now it's solving now, and after we can see that after the job is completed, then we can go to the post processing. Okay, now the simulation is completed, and we can also monitor that. We can have a result of that one. So let's take the results, and then let's say the deformations. And now here you can choose U, which is the displacement, and also, for example, we can see this overlay options also. But now we have this uh, displacements, and then you can also the get the plot of this one as shown in the previous first tutorial. So you can get the maximum displacements and other post-processing methods. Okay, and we can also see the animations, and it's now very fast, and we can play with this this settings. So maybe let's say let's decrease this this frame rate, but you yeah, so we can see the deformation of the beam. Okay, so now we can in the tutorials, and we have this post-processing of this structural analysis results, and this is the end of the tutorial. Thank you, and in the next tutorial we are going to solve the same problem using the structural analysis using cell. So here, if we now see here the 2D temperatures, we have first and this 2D temperatures, and if we now if I see the results for the thermal result here, so we have the temperature distributions in the beam cross sections. So here we have the temperature distributions, so we can make it a little fast this up, and then we can see this temperature distribution in the beam cross section, and we after that one we obtain the we obtain we obtain the thermal response, and then after that we have the we have the structural response of the beam. Okay, that was extra information in the tutorial, and yes, now we finish this tutorial. Okay.